So generally, one commonly used routing protocol that you come across, whereas RIB would be more of a decentralized distant vector routing protocol. If I'm not mistaken, RIB is not widely used these days because of issues of reliability. I'm pretty sure that is one of the reasons why uh, they came with a version 2, which is supposed to be much more efficient and effective in understanding its neighbors' states, so you can determine the most effective link cost associated to a given neighbor to help move packets across it much more efficiently. But generally, you don't. I think OSPF and the link states is much more widely used as compared to the um, RIP version 1 or version 2. Um, so anyway, keep that in mind. So within the global setup and the link state algorithms, the most reliable or most commonly used routing protocols, which relates to intradomain routing protocols, is the OSPF, which is the open shortest path possible, and whereas the decentralized one, which just revolves around distant vector, where we just need to know the conditions of our connected neighbors, RIP is much more widely used at that level. In terms of algorithms, there are a couple of widely used algorithms that we'll look at very soon that relates to the two classifications that we have so far, or we looked at so far. Global, in terms of link state algorithm, uh, the distro is one of the most widely used algorithm to help understand the complete topology link for a given network for a router. And then when it comes to the distant vector route algorithms, we'll look at the Bellman-Ford algorithms. Okay, but that's on the way. We're going to get to that for later. So moving on, um, other classifications are static routes and dynamic routes. Static routes relates to route changing slowly over time, whereas dynamic routes relates more to change of routes more quickly and very periodic updates to respond to link cost changes within a given network. So the classifications, yeah, we have two of them. We do have the global, decentralized, global for link state, decentralized for distant vector, and for static and dynamic, we do have a slow change over time for static, and then more or less rapid changes or quick changes and quick updates or periodic updates for dynamic classifications. Now, other ways that routing protocols are looked at in terms of helping us, understand the current state of our network before we actually move packets across them, so we can implement the right algorithm for it. We also look at unicast routing protocols um, and how essential they are to, different organization setups. They probably do employ the static and dynamic routes. So unicast routing protocols. The round table can be either static or dynamic in this sense, which means part of the second category of the classifications of routing algorithms. Within the unicast, you have either dynamic or static routing tables, where static table is with manual entries, whereas dynamic is much more updated automatically whenever there are changes within a given network or the internet. So routing protocol will be a combination of rules and procedures that lets routers within the internet inform each other of changes as and when they come up. So that will be the key definition of routing protocols. Autonomous systems also play another role in determining routing protocols. Um, in autonomous system, we're talking about more of domains that are set up by various routers or that are administered. Sorry, we're talking about autonomous system being network domains, which involves sets of routers or networks administered by single organizations. Like for instance, assuming that GTUC wants to go enterprise, a good um, uh, routing protocol that it can employ in helping its or routing system protocol that would require that it would need or that it can employ to address how it manages its entire networks of various satellite campuses or whatever. Autonomous system could be a good approach to handling that, where we create our own domain and have our own set of routers that are interconnected, and then we administer it as a single organization. Okay, uh, big organization, big corporations. I'll probably say at Microsoft, IBM, Facebook, uh, some of our social media, Google, and what have you. They'll have autonomous systems, um, routing systems that they use to manage their entire network because it means obviously they feel like they are an entity that controls a huge uh, part of a given network. So ideally, it's very prudent for them to have their own system where they manage their own network. So they can be able to provide better services to their users or subscribers much more efficiently and reliably. So autonomous systems are one of the key ways to go if organization wants to manage its sets of networks or routers uh, autonomously or completely by themselves. So popular routing protocols that you'd come across in looking at addressing routing needs, um, we have the intradomains and then interdomains. Like I was pointing earlier on with the classifications, we do have the distance vector and the link state routing algorithms, and RIP plays a key role in the distance vector, whereas OSPF plays a key role on the link state. So within a distance vector, we're looking at more of how routers only need to know the states of their neighbors only, not the entire network topology. They only need to know, hey, which neighbor am I connected to? What's the state of that neighbor? So in terms of forwarding packets, I can easily forward that packet to that given neighbor easily without having to deal with the entire topology of a given network that I find myself in. On the other hand, though, when it comes to the link state and that the global OSPF plays a key role over there, and that's where we need to know the entire topology, which determine how to move packets much more efficiently. Um, Generally, a lot of people say link states are much more reliable than distant vectors, and I can understand why, because with link states you can you use a router tends to understand the entire uh, net topology at every given point in time, and when that changes, there are uh, updates very frequently. So you have much more efficient and effective or reliable way to move packets across that given network much more effectively as compared to just knowing the state of only your neighbors. You know, if you were to illustrate this using uh, you come into to work and you only use one path on a day-to-day basis. So if there's a problem on that path and various routes on that path don't inform you about it, you might get caught up in traffic, and end up heading to work late if you're adapting the distant vector. But if you had the link state, then instantly be alerted about condition of the router you use to move to get to work on a day-to-day basis. So you know which other the uh, diversions or detours to use to get to work without actually, um, getting locked up or stuck up in traffic on that particular route. So, like I said, it makes sense that link states are much more uh, implemented on most intradomain networks. And then we do have the interdomain networks where we use path vectors. So intradomains are more like your intranet setup within your own uh, contained network or domain, whereas interdomain is more of the internet. So this is where you'd have path vectors that revolves around protocols like border gateway protocols or BGPs. And if I'm not mistaken, you do have uh, other renowned protocols as well that goes with the interdomain routing protocols. But generally, these are some of the key popular ones that you'd come across. So you look at it from, intradomain and interdomain. Inter means interconnected networks, while intra is more of just a small interconnected networks or manageable networks as compared to your internet at as the interdomain network. Okay, so moving on, we want to look at the link states. What the categories. We have the link state and a distant vector. We want to look at them very carefully, a bit close look at them, so at least we can understand them much better and know what kind of algorithms makes up the plays a key role in the implementation uh, on a regular basis on most routers, basically. So with the link state, keep in mind we need to know each node in the domain that has the entire topology of that domain. Keep in mind with that group for the classification, when it comes to link state and the global, we need to understand the entire topology. It's very important we understand the entire topology that a particular router finds itself in. So it's not just your neighbors, but other neighbors, also all their neighbors as well. You need to understand their states at every given point in time. So at least you can have better informed measures on how to route packets much more efficiently within a given network. And one of the key algorithms used is the Dijkstra, the most famous algorithm on the link state routing is the Dijkstra uh, routing algorithm, which we'll look at very quickly. So you do have the link state. Each node in the domain has an entire topology of the domain, and then the nodes can use the Dijkstra algorithm to build their routing tables. So it could be like an analogous of uh, a city map. So here is like an analogous for city map that illustrates the concept of a link state routing, where you do have we have 1, 2, 3, 4, 5 nodes that are within this particular networks. And if we're going to implement a link state routing using the Dijkstra algorithm, it's very important that uh, node A knows everything about its neighbors as well as its neighbor's neighbors, or basically everything, the link states of all the various nodes from A to E within this given network that we have. So we do have a way of going about that. So at least through using a cost or uh, link cost to help us put a metrics to how we determine the various states of all the various nodes within that given network. And we do that by assigning numbers, which are metrics for cost, representing that cost involved in routing a packet from A to B. In this case, is 5. A to C is 2. A to D is 3. C to B is 4. B to E is 3. And then you do have C to E being 4. But when it comes to moving a packet from A to E, you notice that we can either go through A, B, C, or A, C, E. But since route is all about finding the most reliable and efficient least cost or good path of moving packets from a source to destination, we have to look at the most least cost metric that would help us move a packet from A to E. In this case, it will probably be from A to E, because it's A to C carries 2, C to E carries 4, which is 6, as compared to A to B and B to E, which has got 8. So obviously this has got more or less a higher cost as compared to a higher cost matrix as compared to from A to E, A, C to E. Are we following? So we have A, B, E having a higher cost matrix for moving a packet from A to E as compared to using a path that goes from A, C to E, which has got a 6 cost matrix as compared to the 8 on the other side. We good? Oops. So there's a key knowledge of how a link state learns about its routes, so you can be able to forward packets across them. So if you notice in this with A here, it has pretty much a good knowledge of all the various neighbors that it's connected to, as well as their uh, state as well, or their link state as well. So you can be able to basically understand how to move packets across this network much more efficiently. So how do we determine the link states? Various strategies are deployed. One of them being we send information to all nodes, not just neighbors. So if we want to understand how the links informations are identified within a Dijkstra algorithm and a link state, we have to know all the states, every single node within the network, not just the neighbors. And one of the strategies we use to address that is by sending messages to all nodes. So if there are issues coming up or issues happening within a given node or a given side of the network, it's the job of that particular node that's around, that's basically connected to that particular link or that particular link. It's the job of that node to inform the other nodes within the network about the status of its links. So information about directly connected links, not entire routing tables, are very essential. To making sure the informations that are centralized within a given node is looked at, is well informed. We also do have link state packets where IDs of nodes are created, and then costs of links for each directly connected neighbors are assigned, and also using sequence numbers and time to live to handle the state of packets that are being moved across a particular link within a given network. So generally when packets comes through, they assign some of this information, either IDs, or the link state of the packets, the cost involved in moving a packet from a particular link, sequence numbers, and the time to live, which is more or less a time allocated for the packet from a source to a destination or from a link to another link. So when this time to live expires, we can know whether we can identify issues like whether there was a packet drop, a loss of packets, or information lost, or whatever within the particular transmission. So time to live is very essential in helping us understand whether packets were delivered successfully or not. Other strategies includes reliable flooding, where we store most recent link state packets to help us understand how each node's links so each node status is. So we do have a reliable flooding where we store most recent link state packets from all the various nodes. So at least we can forward that information to all nodes and not just the ones that sent it. We also generate new link states packets periodically by incrementing the sequence numbers. Sequence number usually starts from 0 when system reboots, and it decreases at a decrement of time to live for each stored link state packet, and it's scattered whenever time to live is 0. So this will probably be the algorithm for handling the reliable flooding for link state strategy. Now calculating the shortest path when it comes to link state, and at least the cost involved. Like I said, link state deploys or employs the Dijkstra algorithm, which is one of the most famous algorithm used on most routers to handle most link states routing protocols. So we want to take a look at that real quick and see how it works out in helping us understand the link state of a given node within a given network, within a huge a robust network. Okay, so the Dijkstra shortest path algorithm. By the way, Dijkstra is all about shortest path. Okay, when it comes to link states, it's all about finding the shortest path, like find the shortest route to move a packet from A to B. That's what this algorithm is all about. It was very, very well implemented, well written, and so far has played a key role in helping move packets across the internet very, very widely and very, very effectively. So it's been adopted by a number of routers across the internet to help move packets much more efficiently within the shortest possible path. I wanted to look up some research on if there's another much more faster link state algorithm that we can design. Maybe a research at a PhD level. That would be a good research. If you can come up with a new routing algorithm that has got the most fastest, shortest path algorithm for routers to. I think if somebody can design the next shortest path algorithm protocol, so algorithm, that would be very, very probably make that person a bit famous and bit maybe richer. I don't know. it would be a good uh, project topic, dissertation to work on for a PhD, where you come up with a new routing algorithm for calculating routes with the most effectively shortest path algorithm. Anyway, just thinking out loud on that. It's a PhD, uh, project, someday topic or whatever that you want to undertake. Should be fun if you can come up with that. But you'd have to really do some in-depth research because Gistra has hold on to its ground for so many years now, and I don't see it, releasing its script now. Like I said, if you want to pursue that, come up with something new, at least add to knowledge, the body of knowledge, it'd be a cool project to undertake, or a good, topic to undertake. Implementing a new route calculation shortest path algorithm that's not or different from the distro shortest path algorithm, or something different, something new. Anyway, just me thinking out loud. So execution of a distro algorithm, let's look at it very carefully. We do have a network of 1, 2, 3, 4, 5, 6 nodes, with all of them having a cost matrix assigned to their path, and want to build a routing table to help us understand how effectively, efficiently uh, we can move packets from one node to another, or to the fattest mode uh, of our network, using the most least path or the shortest path possible. So to start out with, we have to build an iteration. In this case, our iterations start from 1 to 5. That is more or less the number of sequence that we have to go through in order to cover the entire network or nodes that we have, so we can understand every single uh, node within that given network, not just the neighbors that we have. So we do have the iterations or the sequence, and then we do have the n, which represents the uh, links that you have to route a given packet in. So to start out with, and obviously we have your destinations. We have destination 2, 3, 4, 5, and 6, which covers from 1, 2, 3, 4, 5, and 6. And if we're to be using a link state where we fall solely on just node 1, the question is, how do we move, or what will be the least path that would help us move the packet from node 1 to node 3, or to node 2, or to node 4, or from 1 to node 6, or from 1 to node 5. Okay? So if we do have only one node to work with as a link to use for our transmission, then it's pretty obvious that if we want to get to destination 2, we only have this path to take with a cost matrix of 3. So we do have 3. Then when it comes to destination 3, we do have a cost matrix of 2. For destination 4, we do have 5. But since we only using only one node, or they say more or less, we only have one node at our disposal, or one link, in this case node 1 at our disposal to forward the packet, then there's a high probability that we cannot get to node 5 and node 6 yet. Okay, so at these initial iterations we can't get to these two nodes because we need to